Hello everybody, so this is the second video for chapter 4 of the Introduction to Quantitative Finance course. So we're gonna pursue on the topic of portfolio optimization here. So we're gonna propose our first portfolio optimization problem for which we're gonna derive the solution. Okay, so we're gonna work as we mentioned in the previous videos, in a mean variance framework where we want to identify a portfolio for which we want to have the lowest possible amount of risk quantified by variance, but still ensuring we have a minimum level of profitability for this portfolio, which entails setting minimum levels of expected returns for that portfolio. So we're gonna in this video we're gonna define the problem and solve it, but before that we're gonna present some auxiliary results which we'll need to make sure the problem we propose makes sense. So first we're gonna introduce the following result, which says that for any value m for the expected return, we can indeed find some portfolio which has this expected return m under very mild conditions. Okay, so let's read the proposition. Assume that in the market there exists at least two assets, J1 and J2, for which their expected returns are different. Then for any m in R, so any real number m, there exists a portfolio W. So here W is the weights of the portfolio, which, as we mentioned earlier, represents the percentage invested in each of the respective assets that can be traded, such that the expected return of the portfolio is equal to M. Okay, so for example, if you want a portfolio whose expected return is 40%, you can find this portfolio. If you want a portfolio whose expected return is 5%, you can also find such portfolio. So the idea here is that portfolios with very high expected return, of course, they will have very high risk. Okay, so there's no free lunch here. It doesn't mean that you can magically make as much money as you want without getting any risk. So very high return means very high risk also. So let's prove that statement. So for a given m, the value of the expected return that we'd like to have, there exists a constant alpha such that m is equal to mu j2, expected return of the second asset, plus alpha times mu j1 minus mu j2. Okay, so we claim that this constant exists. Well, in fact, it's pretty simple to derive what this constant would be. This constant would simply be alpha is equal to m minus mu j2 divided by mu j1 minus mu j2 here. Okay, so if we set alpha equal to this value where the denominator is not 0 because of our condition here that we assume, then we have that m is equal to this guy here, and distributing alpha, this is equal to alpha mu j1 plus 1 minus alpha mu j2. So we can see that m is a combination, linear combination of the expected returns of both assets, where here the sum of the coefficients, linear coefficients, is equal to 1. So because the coefficients sum to 1, they can be used as weights to construct a portfolio. So if we set up the following portfolio, a portfolio which contains a weight of alpha for the asset J1, a weight of 1 minus alpha with for asset J2, and 0 otherwise, then the mean of that portfolio, or expected return, of that portfolio would be the weight of the first asset times the expected return of the first asset plus the weight of the second asset times the expected return of the second asset, which is exactly equal to m, which concludes our proof. Okay, so for any value m, there always exists some portfolio whose expected return is m, and the only condition for that is that in the market there exists at least two assets whose expected return is different. Okay, so if all assets have exactly the same expected return, this result wouldn't work. But in practice, of course, there are always assets whose expected returns are different in the market. Okay, so here what we will do next in the portfolio optimization problem we're going to propose is that we're going to set a target value for the expected return. So we're going to say we're going to seek across all possible portfolios whose expected return is m, and among all these portfolios we'll try to find the one which has the smallest risk. And here, to quantify risk, we're going to use variance. So basically what we're going to do is we're going to set expected return of m as a target and choose among all portfolios which have an expected return of m, choose the one which has the smallest return variance. Okay, so for a given amount of profitability, we want to identify the portfolio which has the smallest amount of risk. Okay, so why variance as the metric to represent risk? Okay, so clearly variance represents the variability of the portfolio, and the portfolio who fluctuates more wildly is clearly more risky. Okay, so this makes a lot of sense, and furthermore, we're going to see in what follows that the variance is very tractable. So using this metric allows to obtain a simple formula which will solve our optimization problem. Okay, so this is good about variance, but are there drawbacks associated with the use of variance? The answer is yes. Okay, so in a subsequent chapter, we're going to discuss properties of risk measures and become aware of limitations of the variance. Okay, so we're going to introduce other risk measures called, for example, value at risk, semi-variance, etc. But these are much less tractable in the sense that we typically don't have a simple formula which is the solution of the optimization problem. So this complicates the application in practice. Okay, so we won't discuss entirely drawbacks of the variance now because this will be done later, but to let you know, variance so if a portfolio has, for example, scenarios where the return is very, very, very high, then this will have or much above the mean, then this will have an upward pressure on variance. So high variance can be caused by either high downward risk or high upward risk. And high upward risk would be a good news. So if you use variance as a criterion, you might be penalized these very high, highly positive scenarios, which is not desirable. But for now, we're gonna accept that variance is not perfect and still pursue with that metric to quantify the risk of the portfolio. Okay, so the idea here is to get a low variance. We seek at profiting from the diversification within the portfolio. Okay, so this is common knowledge that very well diversified portfolios have less risk. Okay, because if one stock goes up, then another one might go down, and then on average the movement might partially cancel each other. So using diversification is a very good way to achieve reduction of the variance of your portfolio. But now So to do that, we should rely on assets whose correlation are either low or negative, because movements of one must be able to compensate the movements of the price of other assets. So, okay, this is intuitive. We must rely on diversification, but now we're going to see next how to optimally diversify so as to uh, minimize risk, yes, but still retain uh, our target profitability. Okay, so now we're ready to pose the mathematical problem which we're going to solve. Okay, so the portfolio optimization problem which we propose is the following. We want to find across all possible portfolios. So portfolios are represented by all possible weight vectors, which are in numbers in Rn. So for each asset, there's an associated weight. So when we minimize across all possible set of weights the variance of the portfolio return. So KW, recall it's the portfolio return. So we'd like to minimize the variance, but we have two set of constraints, or two constraints. The first constraint is that the weights must sum to 1. Okay, so here we said the weight vector is a number in Rn, a vector in Rn, but not all vectors in Rn are valid, because weights, they must sum to 1 in portfolios, as we've seen earlier. So we include that constraint for W to represent a valid portfolio. And second constraint, we're going to impose that the expected return of the portfolio is M. Okay, so we fix the profitability that we want, the expected return, and we want to look across all such portfolios, which is the portfolio which minimizes the variance of the return. Okay, so here this constraint, weights must sum to 1. Recall this is the weight vector is a column vector, so when we transpose it, it becomes a row vector. And this one here, it's just a column vector. The boldface one, it's a column vector containing ones. Okay, so in practice, you might be wondering what M we will use. What we will see next is we can repeat the experiment for various values of M and see what happens. Okay, so right now we can take M as fixed, but later on we will see what happens when we consider different values of M. Okay, so the previous problem we saw is a constraint optimization problem. So we want to minimize some function or some objective function under constraints. So from your calculus class, you've seen that such problems can typically be solved through Lagrange multipliers. So we won't review Lagrange multipliers. It's your responsibility to go back to your calculus class and or you can go on Wikipedia and get familiar with them. But so we will assume that at this point you're already familiar with the technique, and we're going to simply apply it here. So in that case, when we use Lagrange multipliers, we must consider what we call the Lagrangian. And this quantity is the following. So the Lagrangian is denoted LW. Okay, so L stands for Lagrangian, W is the variable that we are trying to optimize. This is the gradient of the objective function with respect to the parameters we're trying to optimize. So the gradient, it's the vector of all partial derivatives with respect to each parameters, minus lambda 1. So here lambda 1 is the first unknown constant known as the Lagrange multiplier, times the gradient. And here we use the first constraint. Okay, so we use the quantity that must be set equal to 0. Okay, so since the expected return must be equal to M, then this difference must be equal to 0. So then we do minus the first Lagrange multiplier times the gradient of what must be equal to 0. And since we have a second constraint, there's minus a second Lagrange multiplier times the gradient of what should be set equal to 0 and the second constraint. Okay, so here Lambda 1 and lambda 2, they are constants to be identified in the optimization later on. And here, why do we define this Lagrangian? It's because for optimality, okay, so to get optimal values of W, there's a necessary condition that is at the optimal W, the Lagrangian, or sorry, I pronounce sometimes the French name because Lagrange is a French name, but Lagrangian must be equal to 0 at the optimum point. Okay, so this condition in general, it's not sufficient, but necessary. Okay, but here we won't try to show that it's a sufficient condition. We'll only assume that when we find the point W where the Lagrangian is 0, this is our solution. Okay, so here, Lagrange multipliers, our strategy to find the optimal W is to define the Lagrangian, which is the gradient of the objective function we're trying to minimize, minus Lagrange multipliers times the gradient of the quantities, which must be equal to 0. And then this, we're going to set that to 0 and find the W and Lagrange multipliers alpha 1 and alpha 2, which solve this equation. Okay. So, as we mentioned, I expect you to read the math primer before going through these proofs. Okay, so if you haven't read the math primer slides, it's time to do so. Okay, so we recall from what we've seen previously that the expected return is W transpose mu, where mu is the vector of returns of each respective asset in the market, and variance of KW, the portfolio return, was equal to W transpose CW, where C was the covariance matrix of returns on the various assets. So now we're going to apply vectorial derivatives result, which were explained in the math primer. Okay, so here, the gradient of the variance of the portfolio return, it is the gradient of this quantity here, so W transpose CW. So this is a quadratic form with respect to the vector W, and this expression in the math primer, we've shown that differentiating this expression is equal to 2 times C times W. Okay, so we see here why using the variance is convenient, because the variance can be of the portfolio return can be expressed as this quadratic form, which is very easy to differentiate in practice. So this helps us finding the solution of the problem. Okay, so now we have the gradient for the objective function for the variance. The gradient for the expected return is the gradient of, as we just said above, W transpose U. And in the math primer, we saw that the gradient, vectorial gradient of this expression is simply equal to mu. And finally, the gradient of the other quantity here, W transpose 1. So this whole guy was in the constraint to ensure that weights must sum to 1. Well, this constraint, when we calculate its gradient, once again, it's simply equal to the second vector here, which is a column vector of 1. So if we do that, we can make all these three substitutions in the previous equation. And here the previous equation becomes the variance, which is this guy, minus the first Lagrange multiplier times the gradient of the first constraint, which is mu, minus the second Lagrange multiplier times the second gradient of the second constraint, which is a vector of 1, must be equal to a vector of zeros. Okay, so this allows us to identify the value of W in terms of alpha 1 and alpha 2. So how do we do that? Well, all the terms which don't depend on W, we can throw them on the other side of the equality, divide by 2 on both sides, and then once we have CW is equal to something, we can multiply to the left by the inverse of C. So here this once we multiply by the inverse on both sides of C, to the left, it becomes W is equal to alpha 1 over 2 inverse of C vector mu plus lambda 2 inverse of C1. Okay, so this gives us a relationship between the vector W, the vector of weights W, and Lagrange multipliers. So are we done now? Because this seems to be the solution. Well, we're not done yet because we don't know what are the values of the Lagrange multipliers at the optimal point. So this is what we're going to do next. Identify the values of lambda 1 and lambda 2. So to solve for the values of Lagrange multipliers lambda 1 and lambda 2, we can substitute the value of W here that we've just identified previously and the two constraints of the problem. Okay, recall the two constraints were that the weights must sum to 1 and the expected return of the portfolio should be equal to M. Okay, so here we go back one slide. Let's copy this formula. So W is equal to this guy. And we're going to plug this value of W in the two following constraints. So here the first constraint was that mu transpose W should be equal to M. Okay, so this is expected return must be equal to M. Second constraint is that the sum of weights must be equal to 1. And then we can replace W by what we just had in the previous slide. So if you make this substitution, you end up with these expressions here. Okay, so basically all we did, this is exactly the previous expression for W, but here we multiply each term by mu transposed here. Okay, and recall lambda 1 and 2, they are one-dimensional constants, so they can be taken out in front of mu. And then we can do exactly the same thing with the second constraint. So this is exactly the value of W we had in the previous slide, where we multiply the quantity by the vector of 1 transpose. We made that multiplication to the left here. Okay, so this is good. And now this gives, okay, so here, first, these quantities, they're one-dimensional. Okay, so let's see that. Let's illustrate that. So the vector mu is 1 by n. So here transpose it, it becomes, mu is n by 1. So transposing it is 1 by n. Then the matrix C inverse. C is n by n, so its inverse is also n by n. And here mu, as we said, it's n by 1. So when we make that product, the whole entire thing becomes 1 by 1, so it becomes a scalar. Okay, same thing for all these quantities. Although there are vectors and matrices in these expressions, the dimension of all these quantities is 1 by 1. Okay. Okay. So now this becomes a system of two equations, two unknowns. Okay, so the unknowns here are lambda 1 and lambda 2, and we have two equalities. Well, this is enough to find the solution for lambda 1 and lambda 2. Okay, so we can write this as the vectorial system of equation. So it's here instead, just for convenience, instead of being lambda 1 and lambda 2 being the unknown, we consider lambda 1 divided by 2 and lambda 2 divided by 2. Okay, so we basically attach these twos to their lambdas. So in this case, this system of equation can be expressed as this. So here m and 1 is the vector on the right side. Then the lambdas are the unknown vectors. And here we can form a matrix M here, which contains 4 1 by 1 expressions. Okay, so basically this can be solved simply. So basically the vector lambda 1 lambda 2 by 2, it's basically equal to m inverse m1. Okay, so at this point, we could just obtain the values of the lambdas through this equation. Okay, so in principle, we could say, okay, we're done. But next, what we're gonna do, instead of just using this way of finding the solution, we're gonna solve this system of equation with what we call the Cramer rule, which will give us an explicit representation of the solution. Okay, so here there's this M inverse business. Well, in case of a 2 by 2 matrix, M is not very complicated in practice, but still finding an explicit expression for the solution is always nice. Okay, so this is what we're going to do next. Okay, so let's recall what we call Cramer's rule in linear algebra. So once again, I assume that all of you have followed at least one linear algebra course and that you should already know about Cramer's rule. Otherwise, please go to Wikipedia or any related or any textbook dedicated to linear algebra to study this algorithm. Okay, but if you haven't, well, I'm just gonna briefly give the results so you can still follow it without having to refer to the previous references. Okay, so what's Cramer's rule for solving a system of linear equation? Cramer's rule says the following. So if we have a system of equation of this form, ax is equal to b, where we know a and b, but we're trying to find the value of x, where x is a column vector of n elements, b is a column vector of n elements, and a is an invertible n by n matrix. So the solution, as we said, it's x is equal to a inverse b, but there's also the following representation for x. xi, the ith element of vector x, can be shown to be equal to the determinant of ai divided by the determinant of a, where ai, it's a new matrix that we define by taking the matrix A and replacing its ith column by the vector B. Okay, so A, for example, let's say A is A1, A2, A3, A4. Let's just have something like that. And here, let's say vector B is B1, B2. Then, for example, A1 would be equal to B1, B2, A2, A4. Okay, so we basically, A1 is basically the matrix A, where we replace the first column here by the vector B. Similarly, you can define B2, B3, etc. until Bn. Sorry, An. A1, A2, A3, all these matrices A by substituting the jth column by vector B. Okay. So this is Cramer's rule. Okay, what we're going to do next, we're going to simply apply this Cramer's rule to identify the solution of our system of two equations. So we're going to assume that the matrix M, which we defined previously, is invertible. Okay, so let's not consider pathological cases where M is not invertible. Let's just assume M is invertible here. Okay, so this will lead to the following solution. So let's go back here. Here, this is the system of equations we wanted to solve. So the matrix M acts as the matrix A in the Cramer rule. This is the vector X. So the vector X contains lambda 1 over 2, lambda 2 over 2, and this is the vector B in the Cramer rule. So here, this is x1, which is lambda 1 over 2, by the Cramer rule, it's the determinant of M1 divided by the determinant of M. So this is matrix M, where we replace the first column by the vector B here. And similarly, we have lambda 2 over 2 is the determinant of M2 divided by determinant of M. So here, as we explained earlier, this is the matrix M we defined, but where we replace the first column with what we call the vector B. The vector B had an M and a 1 here. And matrix M2, it's once again our matrix M we've defined, but replacing the second column with the vector B. Okay, so here it might be useful for you to sometimes pause the video and at least have a sheet with you to write the things to make sure you understand well all the substitutions we've made. Okay, so please don't be afraid to pause the video and follow with the sheet and with writing the equations to make sure you understand what we're doing. Okay, so this gives you the solution for lambda 1 and lambda 2. So then this leads to the following solution. Okay, so once we've identified these values of lambda 1 and lambda 2, we can plug them in the previous equation, which was the solution of the weights vector. So let's go back to this equation 1. Let's go back a few slides. So here, this was the equation 1. Equation 1 gave the solution. So it says the weight vector of the optimal portfolio has this form here. What remained to be calculated is the Lagrange multipliers, but then with the Cramer rule, we just computed their values, so we can just substitute these values of lambda 1 and lambda 2 with what we've just calculated, and this gives us the final proposition, which is that the optimal weight vector, after making this substitution, is given by this expression. It's 1 over the determinant of M times the determinant of M1 C inverse, so covariance matrix of assets inverse, mu plus determinant of M2 C inverse 1. Okay, so this is good. We're done with that problem. We have identified across all portfolios who have an expected return of M, the one which has the smallest variance. And this is the formula for the weights associated with this portfolio. So here, what is the variance for this optimal portfolio? Well, recall, okay, the variance of a portfolio. So the portfolio return, we said it's W transpose K. So the variance of the portfolio return here is equal to W. Okay, so this again, this formula is in the preliminary slides. This is W transpose times the variance of their returns times W. So here, for the optimal portfolio, we've identified W is simply replaced by the optimal weights. So you can take W replaced by W star, the optimal weights, and this gives you the variance of your optimal portfolio. Okay, so this solves our problem of finding across all portfolios which have an expected return of M, the one which has the smallest variance. Okay, one quick detail here I haven't mentioned explicitly, but which is very important, is that here we only considered portfolios without the risk-free asset. Okay, so we've assumed we've invested in only the N risky assets, and we haven't included the risk-free asset of return R in our optimization. Okay, so it's the set of all portfolios which only invest in the risky asset, not the risk-free asset. Okay, so because otherwise all these the invertibility assumptions we've made about, for example, the matrix C, it wouldn't work. okay, if you had a risk-free asset because you have no variance. Okay, so here we've only considered portfolios consisting only of risky assets. Okay, so now we've found the optimal portfolio and its variance for a given value of M. But now what we can do is we can repeat this experiment for many values of M and see what the optimal portfolio and its variance look like. Okay, so this allows to define what we call the minimum variance line. And the minimum variance line is the curve M versus so this is the standard deviation, not the variance. So square root of the variance of the optimal portfolio, which has an expected return of M. Okay, so we can make the following plot. We can have M here, the expected return, as the y-axis. And for the x-axis, we can plot the standard deviation of the optimal portfolio, which has a expected return M. And here, it is possible to show under mild conditions. So again, here we won't make all these proofs, but these proofs can be found in the textbook I referred to at the beginning of the chapter. Under some mild conditions, the minimum variance line has the shape of a hyperbola. Okay, so you have a curve like this. Okay, so this picture is directly taken from the textbook. I want to acknowledge that I didn't make this plot, I just took it from the textbook. Okay, so here MVL stands for minimum variance line. So here, this curve here, it represents for all values of M, for all values of the expected return, what is the associated smallest possible variance across all portfolios. Okay, so for example, if M is equal to this value, then the smallest variance attainable is here. It would be this. Not variance, but standard deviation. It would be this value. Okay, so here all other portfolios which are not optimal, their value falls somewhere within the gray region. Okay, so it means that for a given value of M, so let's say this value of M, this is let's say this value of M, this is the optimal portfolio. So across all portfolios who have an expected return of M, this is the standard deviation of the optimal one. And then for all other portfolios which have this expected return, their standard deviation falls somewhere within the line. Okay, so the gray region represents all suboptimal portfolios whose variance is larger than the one of optimal portfolios, and this curve here represents the set of all optimal portfolios, or the standard deviation of all optimal portfolios for the various values of M, which is the various values of expected return. Okay. So this is what we just said. All the optimal portfolios, they lie on the curve, whereas all suboptimal portfolios, which have a higher variance than the minimal attainable variance for a given portfolio return M, they lie within the gray zone. One quick note here. If we go back here, there's the tip of the hyperbola here. So this is known as the minimum variance portfolio. So there exists one portfolio which has the smallest possible variance across. If you look at all values of M of the expected return, each have an optimal standard deviation, but there exists a value of the expected return for which the standard deviation is the smallest. So this is across all, this point here, it represents across all possible portfolios the one which has the smallest standard deviation. Okay. Now, one quick note here is that there are kind of two branches to the hyperbola. There's the upper branch and the downward or lower branch. But in practice, the lower branch, it's not useful at all. So why is that the case? Let's go back here. So these are all optimal portfolios in the sense that for a given their associated value of m, this gives the smallest variance. But it's never intelligent to select a portfolio on this branch here. So why is that the case? It's because if, for example, you draw a vertical line, this says that for a given value of standard deviation, this is all the set of possible expected returns you could get. Okay, so if you want a portfolio standard deviation, let's say this is 10%. So if you want 10%, you'd rather take the portfolio which has the highest possible return than the one which has the lowest possible return, expected return. Okay, so here, for example, for any portfolios in this branch, there exists the corresponding portfolio on the other branch which has the same exact standard deviation but which has a higher expected return. Okay, so for this reason, it's never optimal to select portfolios in that branch here. What makes sense is to select portfolios in that branch instead. Okay. So this completes our first optimization problem. This is the problem of finding across all portfolios containing only risky assets. So the risk-free asset was excluded from our calculations previously. We found the set of optimal portfolios which minimized the variance for a given amount of expected return. So we're going to stop here today, but next what we're going to do is we're going to include the risk-free asset to our model and study what happens. And in a nutshell, we're going to see that although all portfolios in this line, they were deemed optimal in some way, once we include the risk-free asset, it's not all portfolios which will make sense in this line. We're going to identify a precise one in this line which will be more important than the others. Okay, so but this we're going to study in the next lecture. All right, have a nice day.